You know, actually, while I'm doing this, I'm going to give you guys an update on the robot because I worked on the robot the past 2 days. I gave you guys the update on the main brains PC that I bought for it, but I want to give you guys an update now on some stuff I did for its batteries and its first motor. I'm close to getting this thing moving, no joke. So let's go through that next. Okay. Um, Start off with the battery. I'll go through everything I did. I didn't do all the work live. Normally I would. Okay. So I 3D printed this case out of PLA. It's just basically a sleeve for it, and then I slid the battery in. You can see the little spring, and then there's a little knob on this side. And I've got this charger board for it, which is a 1S lithium 18650 charger board, and I got it all wired up properly. And I also wired it to the other one so that if I plug this into USB, it'll charge both batteries. But the way that works would be a short circuit if you don't put a Schottky diode in. So here you can see the blue line I drew from this back one. No, the gray line is where the short circuit happens. So you can see the power comes out of the plus, comes down the gray. These are wired in series, 2 batteries. The gray line comes down, over, up, through the board, into the ground channel of the board, and then over to the other board's ground channel, through the ground of that board. Here's where we need the diode, and then if that diode's not there, it makes it back to the original battery in the back. So it actually travels, because of this connection from the red power line to ground, since the board connects right there, it actually completes the circuit through those gray dotted arrows. So with this diode, it solves it, but it has to be a Schottky diode, which has a low voltage drop, and that solved it. And so yeah, this is our wiring diagram for the 2 batteries wired, the batteries are wired in series, but the chargers are wired parallel to each battery. And so that's how we did it. We could have bought a 2S battery charger, but I wanted this to be scalable potentially to do like 10, 20, 50, 100 batteries. With one of these boards per battery, we would just be able to buy these little cheap like $2 or $1.50 boards to charge each battery, and we could do as many as we want as long as we put a protection diode on each thing. The problem with that diode is because of the voltage drop, it'll never get to the full 4.2 volts full. It'll only be able to reach a maximum of 3.6 volts because the voltage drop of the diode. Okay, so you can see that's how this is all wired up live. I'll show you guys the 3D model I did. I tried to improve it right here. So you can see it's just pretty basic. Let me try to rotate for you. So there we go. Here's a ruler for scale. It's a metric ruler I always use for real life scale, so I can see what's going on. So you can see I put these little things here to put string in, so that I could hang the batteries vertically from the bottom of the robot's rib cage. It's gonna span from the bottom of the rib cage down to the waist, pelvis bone. So basically, instead of a 6-pack, he's going to have batteries where the 6-pack would be. And I've got a model of that here, I believe. So those black things are our batteries. And so because we need them hanging above one another, we needed a way to attach them. And that's why I added this thing. And you can see here how I did it. I just tied it with some upholstery thread string through the 2 loops, so that you can see they rotate. They're still loose, they can still move around. They're not rigidly connected, so they can bend. When the robot bends, they'll bend. Watch. So that's when the stomach bends, these won't hinder it from bending. And you can see that diode we talked about right here. That connection's probably not secure. I'll probably need to reinforce it somehow. I don't like using these little stranded wires and soldering them. They tend to break easily, so I don't know. I'm gonna have to figure out something else for that. But here's the upgraded version. I added a little slot to hold the battery holder tabs. But the problem is the battery ends here, and then that's a lot of space between the battery and here. That's like almost half an inch. I don't think that's acceptable. It can only be like maybe this tall total. So this extra section needs to go. So I don't think this is actually going to work, because you can see from the 3D model, these batteries are supposed to be really hugging each other in order to fit all of them. Unless if we well, I guess we do have more gap here. They just come all the way down to like the penis area. They could tuck back a little bit too into this empty cavity region if they were much longer. So we might be actually okay. But you can see I actually had planned to put them a lot closer. For that, maybe we need to weld battery wire to the ends, because the way we're doing it with the thick wire, these thick silicone wires add a lot of space to this, and then the spring adds a lot of space. Like that's 1/4 inch, another 1/4 inch, or almost a 1/2 inch, and then by the time we get to the frame that holds everything together, I mean, it's just getting too much wasted space here. So I'm not sure. I mean, we might be able to get away with this, but it's not ideal from a space saving point of view. So we'll see. It's kind of, that's gonna, I don't know. I just noticed that just now, by the way. So we're gonna have to possibly rethink this whole thing, because that is not good at all. Well, you know what? We'll probably need to get a battery welder and weld them. This is what I'll do to make myself feel better. These 2 batteries, we'll say, are just mainly used for testing. And this is my little improvement idea, that's fine. But for the live robot, when we start racking together 10 of these vertically, we're going to need a design that gets rid of the space between these batteries. This amount of space between 2 batteries is not acceptable. We need to cut that in half. So we're going to have to figure out a slight improvement on that design. This side's even worse with the spring. So we will be welding with that battery tape. We'll be using this just to weld right onto the battery. We can't use springs and clips and stuff because we have to optimize our space huge for this robot project, because the robot takes up such a tremendous amount of space. Okay, so here you can see the first motor we have sewn into the updated robot arm that used the PVC skeleton. It's a smaller bone structure, but it was super cheap for the PVC skeleton. That's why we had to change to it, because creating all the fiberglass bones was taking too long, and I just couldn't wait. I had to get moving forward quicker than that, and I just didn't have time. We can go back and try to finish that fiberglass version at a future date, but for now I'm building a PVC skeleton robot. So anyways, you can see the output pulley here. This will rotate to draw in the string. You can see it was sewn in with nylon upholstery thread, just sewing it directly into the bone, which is wrapped in adhesive transfer tape and 1000 denier nylon cloth. And then some parts of the bone that needs to be more stretchy, like ligaments, uses compression shirts, athletic workout shirts made of polyester spandex hybrid, and so that makes it plenty flexible for being able to bend stuff. This is the wrist of the robot's hand. So anyways, yeah, we also labeled what each motor is going to. So this is index finger, left and right motion, index knuckle, index middle joint, etc. So this is one of them. It's missing its label, but you can see it's got holes in it for breathability so it doesn't overheat, but we still need to be able to strap it down good. This is kind of a low-tech way to do it. The back side of this has carpet anti-slip painted on so that it grips real grippy, and it's like a rubberized inner so that it grips on the motor tight, and we sewed it on real tight. And the way I sewed it doesn't interfere with the turning of that, but it sews on real good. And this tape was just a placeholder to show where on the bone we want the motor, so we centered it right there. We did all our measurements to match the 3D model. And so anyways, what I did just yesterday was I did the circuitry for the motor controller, and I strapped it to the motor. Well, it's actually not strapped, it's just loosely connected. And I actually connected up the motor, the two ends. You can see they're soldered in. And this is the motor controller board. I made it myself using a motor controller chip and then a bunch of jumper wires. We use solid core jumper wires from this box of U-shaped jumper wires, and we soldered them in to this little breakout board that takes a 8-pin IC SMD style and breaks it out to 8 little through-hole drilled holes, plated drilled holes. And then we soldered each of these in, and we were able to bend them into the direction we wanted. And then I put a little bit of solder on the ends of them just to thicken them up a little bit, and then I plugged them into a normal female jumper housing, so this way I could extend the length without... I think that's going to be a solid connection. It's actually pretty sturdy. You can see it's sturdy. And I could wrap a little bit of electrical tape around it just to protect like whatever little amount's showing, but just as much shows right there, so I don't think I need to. It's actually like a good connection. So that then leads to just here. Now this is green. This is for forward. This will go to our microcontroller. When it sends a signal through this green wire, it's going to cause this to turn forward because of this little IC chip. And then when it goes through this signal wire, it's going to tell it to go backwards. Now, this IC chip had 2 voltage plus and 2 ground outputs, which came out to this board. I believe this was ground and this was ground, and then the 2 voltage inputs were on the left in the center too. And after we connected our wire, we just kind of bent them to point them all up this way, up toward the center of the robot's arm. And then once we were able to go to one of those female housings to a normal jumper wire adapters through this setup that I used, then I switched the color to the traditional black for ground and red for voltage. And we had 2 for each. And so these 2 and 2, so the 4 total wires provide power and ground to this board. And this board then feeds it to here. So this board's basically an H bridge. And let me get the part number for you guys. Well, where did I even put that stuff? Oh, here it is. I'll show you guys the name of the board I'm using. It's called a L9110S H-Bridge Brushed DC Motor Driver Chip SOP8 package, 2.5 to 12 volts, and then 800 milliamps continuous, 2 amps peak current is its maximums. And here's the wiring diagram, and I'll show you guys the breakout boards I bought. It's called a SOP8 breakout board. Comes in a package. It's got one form factor here, and then if you flip on the back, it's slightly different spacing on the pads, so it can handle 2 different spacing styles. It's got the standard spacing, then a little bit tinier. This is the real tiny, and then this is the standard. And we needed the standard. I didn't know they were different on both sides for a while, so I'm glad I found that out. So anyways, you can see how from these little pads, it then goes out to each one of these through holes. Now, we were thinking of using actual header, which is the more traditional route. One of these 90-degree headers, and then just plugging a female DuPont jumper cable to it. But it was taking up too much space. So I'll show you guys. I actually did one like that, and I was not happy with the amount of height that it was taking up on the robot. And as you guys know, I am going to be super greedy about space saving. So look at that. If you look here, it's taking up a lot of space vertically. Whereas the way I did it, I got rid of that. I realized that's not going to work. I did it in a way that takes up much less vertical space. These are almost pressed flat against here, and you can swing them any direction you want. So the profile becomes a lot smaller this way. And this way it doesn't, like that would be the other way would have been sticking out to like here. And now I got it nice and flush against the motor. So we needed that tight fit to keep the amount of space shrunk down, because we need to be able to fit tons more motors on both sides of the arms, and tons of little sensors we'll try to squeeze in wherever, and the air cooling tubing and the water cooling tubing and all the control wires, and we're going to need to fit little microcontrollers like in the wrist areas. Like we're going to be finding little room with like a microscope trying to fit as much stuff as we can, because we need so much stuff on here. We need OP amps and strain gauges and current detector sensors, circuits, and all kinds of stuff. So it's going to be ridiculous how much stuff we need to fit. And so we can't afford to use headers because they take up too much room. So we actually need to use wire directly in. And because this wire is solid core, I don't think it's going to snap off like the braided wire, or the little finely stranded jumper wire. You move that thing back and forth 5 or 6 times and it just breaks. The strands are just too flimsy. And so, and the solder creates a weakness that it breaks right near the solder joint. So with these, it's not going to break, I don't think. It'll last because it's solid core. It's not going to move that much, and it's beefier. And also, the actual connection we do is not using any soldering. It's just press fit inside this housing. So that will also help. This would be the place that's most likely to break at this connection. So since we did it this way, I don't think it's going to break. And yeah, so anyways, after I got the power and ground off this motor controller, I wired it all the way up the arm to almost the elbow joint, and then I put it into temporarily just one of these connectors. We just shoved the 2 power ones and the 2 ground ones in here, and so we'll be able to shove power and ground from the battery, from these big cables, into this side, and then we'll have it live. And all I need to do then is connect these 2 control wires up to my Arduino, and then I can send signal to it, and that will start turning this motor left and right. And then once I've tested different speeds, start, stop, etc., then I'm going to actually wind up some string on here and go through that, and then through some hollow tubing and to the actual joint to act as a muscle. And the hollow tubing we actually have purchased already. I'll show you guys that. That's here. It's the perfect size. This is TPFE tubing, and it actually is a flawless size for this. And so this tubing will stub out near the output pulley, and then it will bend in a tight radius around. We don't want it to bend too tight of a radius, though. That'll provide too much friction. So we'll probably path it like out toward around the center of the wrist, and then curve it like that, and then curve it back. And then it'll make its way up the index finger, and then it'll go to, like, let's say right here, it'll stop there, and then the string will come out of this little pulley, go through the tubing, which will guide the string, and then the string will exit right here, and then actually sew into this index fingertip, and then this fingertip will then bend when it winds up. Now we can put another set of string wound the other direction in between here and here. So we'll have one set of string in between these two, one set of string in between these two. In fact, this is just paper, guys. I put just paper super glued on, and all it does is it guides the string to stay within the right channel. So the other string we'll put in here, it will rotate the other way. When the motor rotates one way, it loosens the string here while tightening the string here, because they're wound up in different directions, one clockwise, one counterclockwise. So that will mean the string that's here will be one muscle, and the string here will be the opposing muscle. Every muscle in the body has a main muscle, then an opposing muscle. So you've got, like, for example, your quadriceps and your hamstrings, they oppose one another. So when it rotates one direction, it will bend the finger down. When it rotates the other direction, it will bend back up. And that will all come from the same motor. So one motor can operate 2 directions on a single joint. And so we needed 4 motors to operate the index finger. And so that's why I put 4 motors in. We'll do this joint, which is forward, backwards, left to right, like this and like this. And then we got the knuckle joint, which is that, and then we got this joint, which is that. And so that's what all these motors are going to do. So these 4 are just for one finger. And as you guys saw from the 3D model, we got tons of motors planned out to go into the arm of various sizes, going all the way up to gigantic motors. Compared to these ones you're seeing here, which is these, you can see some bigger motors for like the wrist right here, and then real big motors for like the bicep, triceps, and some of these motors actually are for the shoulders, I believe. I was actually able to fit them in. So yeah, it's getting exciting when you got the wiring getting done for one of the motors. I'm like just an hour away from getting to coding a microcontroller to make tests on this motor forward and backwards, and then we'll wind it with string and we'll rig the finger and we'll have the finger moving. So all this time 6 years it's been, and we're going to finally have the first moving part 6 years later. Sad, but I mean, that's the pace I'm working at, because all the planning work that goes in, all the engineering, all the electrical engineering, and all the customization, like everything I have to customize, because it's all for a robot that has a lot of very precise needs. This robot needs to have so many parts fit into such a small area that nothing like, you can't use a servo motor. A servo motor has a motor this big in it, and then the rest is just gears, and then it's got a potentiometer built in. It's in a large plastic case, and for just a little motor, that big case, it doesn't work. So that's why we're just using actual motors themselves, and then we're going to make a little potentiometer like squeezed in somewhere where we can find space, and we'll put the motor controller board like we saw strapped onto the side of the motor. We'll get rid of all that gearing, because that gearing makes it too slow. We don't need it. We can use a pulley system, and I actually have a design for a pulley system that's super awesome. Look at this. So here's the motor with the pulley system. You can see it just wraps around a little plastic part and then ties off, and that doubles its strength. Then another string goes from there to here. Here's a close-up. Here's from the motor, goes around that little stick and then ties off, and then another string goes from there to there. And so this is a pulley. It's called a pulley block. Pulley blocks are used for like towing and stuff, and it doubles the force. You can actually wrap it around again and again and like triple, quadruple the force. So just with some little strings and pulley blocks, we can get our motor slowed down or sped up. When you slow it down, you increase the force, but you lower the speed, or you can have maximum speed but lower force. And so we don't need gearing systems when we can use pulley blocks, which can be tiny microscopic little blocks. So that takes up way less space than a bunch of metal geared gears of a metal gear servo. And so that gearbox will reduce weight by getting rid of it, instead of using a little plastic pulley block made of nylon 3D printed, or PLA might even work. I mean, it's so tiny, I don't think PLA will break. Maybe nylon, we'll see. Depends on how big the force is. So little inventions like that are going to revolutionize the ability to cram in all the technology, all the sensors, all the motors into a humanoid form factor. Now, I know people are doing that with prosthetics and stuff at the very highest end, but they're using a very expensive custom stuff. My custom stuff is super cheap. So I'm coming up with budget-friendly way to make this happen, and making everything free, all my designs and stuff. And so yeah, that takes a lot of work to actually design all that, and that's slowing me down. But plus, I mean, other stuff, other hobbies, whatever, real life, all that stuff slows me down as well. But we're making great progress here. Now, I could have sat here and filmed me doing all that soldering of the batteries, but it's like I don't feel it's very necessary. I'd rather just do updates like I just did. I'd be able to teach you just as much. I mean, you guys could see how I solder. I'm not the best. I'm thinking more doing updates and doing a lot of the robot work not live. But like testing we'll do live, and we'll do live updates. But actual soldering, point to point, I might not film that very often. Maybe once in a while I will, but pretty much that motor controller, we're going to be repeating that for like 50 motors. So I might show you guys how I do one of them once I get real fast at it. My first one is going to be horrible. It was trial and error. I actually restarted a couple times. I redesigned it a few times. But once I get it dialed and I'm super fast at it, then yeah, I might show you guys how to do one. But I don't need to be showing you guys how to do soldering right now. I'm slow at that. You say do it live, but here's the problem with that. When I do it live, I spend half my time working, half talking. So that slows down progress by 50%. And we don't want slower progress. We're at year 5 and the robot doesn't even move yet. Now, it might move within the next 48 hours. But that's horrible that you have a robot that doesn't have a single moving part 5 or 6 years in. No, it's actually 6 years in. That's horrible. Like, that's demoralizing. Now, I am very enthusiastic, very, very high confidence that I can do this. I believe in the designs I've made. I'm a hard worker. I just am naturally very optimistic, so I didn't quit. Well, most people, they worked on a robot for 6 years and they still didn't move. They'd say, I give up. So that's why I don't want to do it live at this point. It's like the robot's dragged on too long. Too many other projects keep interrupting. When I do work on the robot, I want to work on it as fast as I can, uninterrupted, and keep the updates to a minimum. Because you guys are sick of updates. Like, maybe some of my hardcore fans still like it, but it's like, how many more bones? How much more 3D design work? We want to see the robot like coming together. We want to see this robot moving. Come on, like, let's get it done. So that's how I feel my audience is at this point. They're either feeling they've given up on me, or they think I'm just too slow. So it's time for me to get serious about making progress faster. So yeah, that's why I'm going to do most of the electronics not live. I'll just do updates on showing what I did. And I'll definitely do a live testing, though, to show you guys it working. So that was a mouthful. That's the update on the robot and on the farm. And so yeah, everything's going good, and very exciting stuff. I worked on the robot like 7 hours just to do that little bit of that little bit of soldering you think would take like an hour. It took me 7 hours. I'm super slow. I have to think it through. I have to redesign it. I'm not experienced. I have to constantly be fiddling with this and that. It can tend to be a mess, but I'm getting faster and faster. And I bought portable soldering station so I can actually babysit the baby while soldering, like on the couch upstairs. This little Dremel soldering gun thing enables me to solder upstairs. It's propane based. No, it's butane based. And so this thing is a game changer for enabling me to work on the fly. The problem is, a lot of times I'll use this also to melt plastic or something, and then it corrupts the tip. No matter how much you clean it, sometimes they get corrupted. So I bought another cheap one, super dirt cheap. This was like $8, and I'm using this one for plastic. So I'll just be able to light this thing up and melt plastic for like sculpting plastic and modifying 3D prints. And then the other one I'll use for soldering. So little things like that might not seem like a big deal, but I've spent like 20 minutes trying to sand down a soldering tip to get it to take flux, or to take a tinning again, because it turned charcoal black from some weird plastic combination. And that's time that's gone forever. And so it's like, I'm just going to buy a dedicated plastic melting soldering iron, since I melt plastic with soldering irons all the time. So little things like that, and the portable setup, so I don't have to move my whole soldering station. I have a little portable station. That's game changing. Like, it's going to enable me to work in the car on the way to church, or work driving to vacation on a road trip. I need to be soldering in my sleep, guys, because I have so much soldering work I need to do. It's ridiculous. And I want this robot moving ASAP. I want this robot bad, guys. Real bad. I want a robot helper to help me do my projects and build more robots. That's been the goal from the beginning. I want it bad. I want a robot to mow my lawn. I want a robot to make me meals. I want a robot to do the dishes. And I know how to do it. I know how to make the AI. I know how to make the motor controllers custom. I know how to make the servos custom. I know how to make custom battery management systems. I know how to make a custom power supply. I know how to make custom gauges and sensors, custom liquid cooling, custom air cooling, custom everything, custom vision recognition, custom algorithms, custom speech recognition. Actually, I don't know how to make custom speech recognition. Everything else I said, I know how to do it. So but I'm planning to do that. I'll figure it out. So, anyways, like, I have the knowledge, but I desperately need to see the progress. I need to see it actually going into practice. And so I'm like super motivated, super excited, super energetic about it. I've taken like a 1 year break from the robot because life got in the way, and now I'm starting to work on it again. I'm excited about that. I don't know how much I'll be able to because of all the other real life stuff, but I'm gonna try to work on it as much as I can. Give Larry more funds, do more projects. I mean, yeah, it definitely helps, I guess. But I'll be honest, like, I'm doing pretty well on funding my projects myself without help. I'm not saying like I don't like having donations. It definitely makes me feel like appreciated, and it just helps me in general. But um, funding's not the issue because the robot took me 6 years to get to this point, and I've been saving little by little. I managed to save up like 1,800 for it. Yesterday or the past 3 days, I've been buying a lot more wiring, and I just bought the main PC for its main brains of the robot, and I spent like $700 in the past 3 days. So now I only have like 1,100 saved, but that's still $1,100 worth of sensors and motors and batteries, whatever we need. And so I feel like I'll be able to keep up on the expenses side of it. But maybe if we need to get into like TIG welding, I still need a TIG welder. If we need to get into solar, I still need solar systems. If we need to start working on some other really expensive project, I'll probably need money. But it seems like I'm doing pretty well. I feel really good about the financial situation I'm in as far as project funding. But blacksmithing, when we start needing to blacksmith pour our own custom metal parts, I will need to buy all the stuff to make my own kiln and stuff. So I haven't saved up all the money for that yet. I only have like $370 saved for that, and I probably need like another 500 for that to have like a really good kiln and forge and all that stuff. And then like I said, the TIG welder, that's gonna be like another 800. I have like 380 saved or something for that. So I've been saving, like I'm getting there on these things. Little by little, I'll put in like $20 on a good month. So little by little, we're starting to put together our tools and supplies and specialized equipment. Um, and I'm a saver, and I make a decent amount of money, and I save most of it by living with my dad and being cheap. But yeah, it definitely does help a lot when I get donations. Even though it's like I can't rely on that because I don't have like that big of a fan base to actually fund everything. So I have to fund most of the stuff myself and work, which is fine. So, anyways, that was the updates. I'm glad I got to tell you guys everything that's going on. It's very good news, right? So I'm excited. And peace out. I'm gonna get back to work.